Hello and welcome to the Computer Vision Festival, hosted by the AI Accelerator Institute, a global community of over 400,000 AI leaders and practitioners, all striving towards one shared goal: inspiring the next generation of machine intelligence. With expert presentations on the festival agenda covering everything from space exploration on Mars to self-supervised learning, you're in for a treat. If you have any questions for our speakers or want to connect with them further, then ask away in the comments sections of the video and hear them answered at the end of each session in our live Q&As. If throughout the day you're loving the content, then be sure to check out the AI membership plans, where you can get access to exclusive content in the form of interviews, reports and articles. Access all areas passes to all past and future events. You can also join our Slack community, which is home to more than 2,500 fellow AI, machine learning and computer vision professionals, and is full of dynamic conversations and contributions. So if you're not already a member, come and join us today. Sign up using the link on the AI Accelerator Institute website. I want to say a massive thank you to all of our sponsors and partners for helping us to bring the festival to your screens today. Our amazing speakers for contributing some awesome content, and to you, our attendees, for joining us today. That's it from us, so go ahead, sit back, relax, and enjoy the festival.
Hi, my name is Lakshmi. I am a team lead in the Software Applications Group at GraphCore. Today, I'm going to talk about how we have scaled training of computer vision models on the IPU. Here's a little about us. GraphCore develops processors and compute systems specifically designed for AI and machine learning workloads. We provide hardware technology as the IPU processor and software as the popular software and development tools as part of a complete solution to enable innovators to solve current and future ML problems. We've launched our first generation of PCIe card-based products, which were delivered via IPU servers. We have now announced our Mark II processor delivered in the IPU M2000 product and IPU Pod rack scale products, which provide scalable deployments that can ramp up into tens of thousands of systems for supercomputing scale-out. At GraphCore, we have co-designed and tightly coupled hardware and software systems for scalable machine intelligence workloads. Ease of use is at the core of our design philosophy. During this talk, I'll discuss how the popular SDK, comprised of common machine learning frameworks, popular programming interface, and the interface to low-level hardware allow ML practitioners to easily scale computer vision models such as ResNets and efficient nets on our Mark II IPU systems. In the next few slides, I will outline the features of our IPU hardware that allow us to scale training of computer vision models on a large number of IPU devices. The IPU is a massively parallel distributed processing engine. Recently, we've introduced a second generation IPU, Colossus Mark II. The new Mark II processor, built with 59.4 billion transistors, consists of 1,472 independent IPU tiles or processor cores, each capable of executing 6 independent workers in parallel for a total of 8,832 fully independent program threads. Utilizing 47.5 terabytes per second of memory bandwidth, each IPU has access to 900 megabytes of on-chip memory, PCIe Gen 4 interface, and chip-to-chip IPU link interface with 320 gigabytes per second of chip-to-chip bandwidth. To support fast distributed compute on chip, we have 8 terabytes per second tile-to-tile communication bandwidth with fully timing deterministic execution driven by compiler support and software. Hardware-accelerated tile synchronization allows low latency messaging of work completion between the tiles, allowing the processor to move between compute and exchange phases. Scaling across devices allows us to support model and data parallel machine learning applications. The IPU exchange model extends off device to support software-driven cross-IPU synchronization. The IPU link technology allows chip-to-chip communication at massive scale, and in order to support scaling across devices, we've built a software construct called a GCD that creates a single large target from applications for supporting both data parallel and model parallel training configurations. Along with scaling across IPU devices, we also support scaling across systems. This allows us to build very large machine intelligence applications on the IPUs. Here you can see how we can create a 256 IPU application target from 464 IPU domains. This can be extended for up to a maximum of 64,000 IPUs using our Mark II Colossus IPUs. Common IPU software primitives support scaling across devices and across systems. We use the exchange primitives and IPU link along with host connectivity over PCIe Express to build massively parallel applications. Recently, we've introduced a second generation IPU pod platform, which allows us to scale at the rack level. They utilize both in-processor and streaming exchange memory and are equipped with optimized communication collectives via the IPU fabric. Disaggregated hardware systems can be reconfigured, allowing flexible application domain targets for machine learning frameworks. IPU machine is our building block for scalable AI systems. Each IPU machine consists of 4 Colossus Mark II processors, offering 1 petaflops per second of AI compute with access to integrated streaming memory, IPU gateway SOC for IPU connectivity, and is fully integrated as a target for machine learning frameworks in our Poplar SDK. To summarize, the recently introduced Mark II Colossus IPU hardware is designed from the ground up for machine intelligence workloads, with a MIMD architecture supporting fast training and inference. 4 Mark II IPU Colossus form the IPU M2000 product that can be stacked to Pod 64, offering 16 petaflops of AI compute. It can be scaled all the way up to Pod 64K, allowing us to execute massively parallel workloads at scale. In the next section, I'll talk about the Poplar software stack and how it enables us to train machine learning models at scale. Our Poplar SDK supports widely used machine learning frameworks such as PyTorch and Onyx via the Poplar Advanced Runtime and TensorFlow through a highly optimized XLA backend. We also provide support for higher level libraries such as Keras and Hugging Face. The next main component of our SDK is Poplar. Poplar contains standard libraries for optimized primitives for matrix multiplication, convolution, sparse operators, random number generation, and communication collectives. These all build on top of the Graph compiler and Graph engine, performing the core runtime capability. Poplar is abstracted away from the underlying hardware via the Poplar device interface, which abstracts away the PCIe-based system and IPU fabric systems. We also support a wide range of platform software ecosystem products for application deployment. Poplar SDK supports commonly used machine learning frameworks such as TensorFlow and PyTorch. So you can get a fully performant IPU target for your current machine learning models using the TensorFlow XLE backend. We support both TensorFlow 1 and 2 with examples and documentation on our website. So we also support PyTorch with some small wrappers around the model and optimizers. And we also have multi-IPU primitive support for PyTorch models. And it's, as you'll see in a few slides, it's very straightforward to take a PyTorch model and replicate it to run on multiple devices. We also have support for Poplar Advanced Runtime, which is a lightweight application runtime that's highly optimized, through which you could run inference and training. It also supports model input through Onyx, and it has a Python and C++ API. Along with support for all these frameworks, we also have extensive documentation in our developer webpage and also code examples walking you through common use cases. Poplar and PopDist are the libraries that support distributed training over the IPUs. Poplar is a command line utility for launching distributed applications. It takes care of acquiring and setting up the IPUs, and it also sets up a virtual IPU partition depending on the number of devices that you've requested. PopDist is a Python library that you could use to configure your application to run multi-IPU jobs. So it takes care of configuring the number of replicas, broadcasting initial weights, and sharding the dataset between the instances. In the next section, I'll talk about distributed training and multi-IPU constructs such as model replication, data parallel training, and model sharding. Multi-IPU constructs such as model sharding, where a model is split across multiple devices, allowing user-driven software control of model parallelism, is fully supported in PyTorch, TensorFlow, and PyPart, along with model replication, which supports the replication of models across an entire IPU system, enabling data parallel training. We also support pipelining of models across multiple IPU devices to extract maximum performance for model parallel execution. To illustrate how we support automatic replicated data parallel training, say you have a very large data set on which you would like to train a computer vision model, and you'd like to use multiple IPUs, in this example, 64 devices, to do the training. In this example, we've set up the IPU domain so that it has 4 instances, each with 16 IPUs. So we're going to run training on the system using a 64 replica IPU configuration. So the underlying distributed training system automatically splits your data set into 4 subsets, each going into a different instance. This data set is further split so that each replica gets its own subset of the data. All of the replicas start with identical weights and process a different subset of the data, known as a mini batch, and compute the loss per batch. They then do the backward pass and compute the local gradients per mini batch. Once we have the local gradients per replica, we perform cross-replica gradient reduction to get the total gradient for that particular iteration. Finally, all of the replicas perform identical weight updates to compute the weight for the next step. All of the steps outlined above happen out of the box without requiring the user to write any custom code to modify their training loop. So the data is split automatically, and then the forward pass and backward pass is executed, and then the mean reduced gradients are computed, and the weight update happens, all with very few lines of change to the actual code base. Next, I'll walk you through the code to show what it takes to go from a PyTorch application running on one IPU to a PyTorch application running on 64 devices. All of the code that I'm going to show you next is coming out of our public examples on GitHub, to which I will link towards the end of the presentation. So say you have a PyTorch model that you've managed to run on a single replica, and you'd like to extend the training so that it goes faster and runs on 64 devices. What you'd need to do is to create a pop dist option, which tell the application how many IPUs you'd like to use per replica. This slide shows you how to take a model that is expressed in PyTorch and run it in PopTorch. All you have to do is wrap that model, vanilla PyTorch model, within this PyTorch PopTorch.training model call, and pass the actual model in the model options that we looked at in the previous slide, and then the type of optimizer that you'd like to use. Finally, within the training loop, you want to ensure that you're computing metrics across all replicas. And since you're doing replicated data parallel training, you only need to checkpoint from one replica. So that's it. Those are the changes that you'd need inside your application to enable distributed data parallel training. Now that we've covered the minimal code changes that we need to run a PopTorch application on multiple devices, let's look at how to actually launch the training. So you could use poprun, which is the command line utility to launch distributed applications, and easily change the number of replicas that your training scheme is using. So just by prefixing this poprun command over your vanilla Python training command, you can achieve distributed training. In this particular case, here we're training over 4 replicas, with each replica being 4 devices, and we're using 4 instances. What this means is each instance has 1 replica, and each replica has 4 devices. Apart from the fact that it is very simple and straightforward to take a PyTorch model running on 1 replica, 1 device, and scaling it up, there are a number of other popular SDK features that support distributed training and make things work under the hood. We support float 16 training with stochastic rounding. So this means our weights can also be in float 16 position, and also our actual compute of forward pass and backward pass is in float 16, as well as our activations are float 16. In order to simulate larger batch sizes, we support gradient accumulation, and recomputation allows us to save memory at the cost of additional compute. We support loss scaling to make up for loss of precision when we do forward pass and backward pass in FP16. Certain neural network operators such as batch norm depend on having a large enough batch size, and to allow for to simulate large batch sizes by aggregating the statistics across replicas, we support distributed batch normalization. We also have support for the newer large batch optimizers such as LARS and LAM that are commonly used when training with very large batch sizes in data parallel training. As you've seen, we have native support for data partitioning and fast pre-processing. We use simple optimizers and wrappers around optimizers to perform synchronous stochastic gradient descent on multiple devices. We have a support for powerful profiling tools, Pop Vision to debug performance issues, and to capture all the low-level timing information, and all the way down from a small Poplar op to how much time it takes for a particular layer to run and how much time it takes for, say, a communication collective to run. We have optimized collective libraries for efficient ring all reduce. And we also have support for easy integration with tools such as TensorBoard, TensorFlow's monitoring tool, and also it's easy to integrate other third-party tools such as weights and biases. Here are some training results. Typically, when you're scaling a model, going from 1 replica to 16 replica, keeping everything else constant, including global batch size, you'd expect to see identical training curves so that you don't have to actually go and tweak any other hyperparameter. You just expect that the training goes much faster, but nothing else changes. And that's what we observe. So training with a single replica or with 16 replicas generates identical loss curves, identical accuracy. So we don't have to do any further optimization or hyperparameter tuning. And here you can see training a ResNet-50 model in TensorFlow on a pod 16, we get about 26,000 images per second, which scales up to almost 70,000 images per second on a pod 64. And all of this is with very minimal code change, just using pop run wrappers to change the number of replicas, allows us to leverage more devices and get training to converge faster. Finally, here are some links to the developer webpage for all our documentation, SDK release information. This GitHub repo has all our public examples, including open source code for our popular runtime, the TensorFlow backend, XLA backend, and all our application examples. This is where I pulled out the PopTorch code example walkthrough from. Docs.graphcore.ai has a lot of relevant documentation, and we are hiring. So if you'd like to work for GraphCore, please do go visit the webpage and apply. And stay in touch. These are links to all our social media and website and email. That's it. Thank you for listening. Happy to answer any questions that you might have.
Hey everyone, so just want to give a big thank you to Laxmi and to our partners GraphCore for that brilliant presentation. And if you have any questions for Laxmi, she is actually here now and would love to answer any questions that you have. Feel free to post them in the chat. We've got a couple of minutes, so take your time, think of a question, and then we'll get around to it. So we've got one here for you now, Laxmi, if you're still there. Hey,
Yeah.
cool. Brilliant presentation, Laxmi. Thank you so much.
Thanks, Jordan.
No problem. So there's a question there from Gareth Stokes. Could you talk about the advantages of the Colossus MK2 IPU over GPUs?
Yeah, so we have detailed benchmarks on our website, which does a thorough comparison, and we see total time to train advantage on large models like BERT and vision models like ResNets and EfficientNets on the IPU. So yeah, I'd encourage you to go check out our website and our benchmark page to get more information.
Okay, cool. We still got a couple of minutes. Is there any other thoughts that you wanted to share, Laxmi, or has anyone got any more questions? Feel free. All questions are welcome. Don't be shy. It usually just takes one or two, and then they all start coming in. Cool. So, okay. I suppose we can wrap there if no one else wants to join in. But yeah, once again, a huge thank you to our partners GraphCore. Huge thank you to yourself, Laxmi, for putting that together. And what I'll do now is I'll post a link to the next session in the chat, and we'll move over in 20 minutes or so. Gareth has just jumped in with one more. So, does the on-die memory help with sparsity?
So yeah, sparsity is something that we're really interested in. We've because of the fact that we have sort of support for doing very parallel compute at fine scale. We do have advantages when it comes to sparse compute, and we have like dedicated sparse computation libraries in Poplar supporting sparse matmls, for instance. The on-die memory helps more with basically giving access to weights at very low latency. I'm not sure it directly helps sparsity, but definitely given the nature of our fine parallel compute paradigm, we are able to support sparsity.
Okay, thank you very much. That looks like it's it for the questions. But yeah, once again, big thank you, and I'll see you all on the next session.
Thank you.
Thanks, Laxmi. Bye-bye. Oh, Pete, we've just missed it. Not unless Laxmi is still there. If you are, Laxmi, there's one more question that's just come in. If not, we just reach out to her on LinkedIn. She'll be happy to answer it.